Okay, so what you're going to see here is my model of an earthquake, and in this model you're going to see why we get seismic waves at the surface and why we get these little squiggly lines on a seismograph. So in this model we have the brick right here, which is going to represent one block. We have the cup, which represents another block. And the fault is that plane of weakness between these two blocks, where the two blocks rub against each other. Before the earthquake happens, we have elastic potential energy that's kind of being stored up, and then after the earthquake or during the earthquake, it converts into mechanical energy, or where we have kinetic and potential energy stored on moving at the same time. As far as forces that are at play, we have friction that wants to keep these two blocks together, as well as other structural things in the rock. But we also have either tension or compression that's going on, that's working against this friction. So tension wants to get these, is the force that wants to get this thing to move, or compression. Friction wants to keep it in place. And so what happens is, as this elastic energy is being built up from compression or tension, we have these forces that are trying to overcome this frictional resistance. This frictional resistance, is due because we've got a lot of friction, we've got a lot of rocks that need to be broken, so they're kind of preventing this earthquake from happening in the first place. Nevertheless, this tension eventually overcomes this friction, and when that happens, we have an earthquake. And watch what happens at the surface as a result of this moving. You'll notice the waves at the surface where we have an earthquake. This is why we get a lot of rupturing or a lot of activity at the surface of the earth during an earthquake. It also explains why we get these little squiggly lines on a seismograph. As you slide it right across, you generate seismic waves which propagate through the rocky material and reach the surface. And as a result, we get the waves at the top. Now, there are a couple things that we look at to examine the size of an earthquake. We look at the rupture zone, or the area that the block moved relative to the other. And we also include the distance the block moved relative to the other, and also the rock's rigidity. Those factors are calculated into what is called the seismic moment, which then is incorporated into a much larger equation called the moment of magnitude. And that's how you get the magnitude 8, magnitude 9, magnitude 7 earthquakes. And all that really is just a comparison of how large that earthquake was relative to other earthquakes. And I hope that made a little bit of sense as you looked at this model, in helping to explain and understand at a deeper level what's going on inside the earth when an earthquake happens. Thanks.